Okay, welcome everyone. Welcome to the second day, and today in the morning, we're very happy to have Nima here. And Nima will tell us about surface kinematics and the integrand for gluon amplitudes. So Nima, you want to take away?
All right. Well, guys, I'm really sorry I couldn't be there in person. I was really looking forward to it, but something came up yesterday, and I can't make it. I was planning, as usual, to give a Blackboard talk. And I didn't have time to make slides, so it's going to have to be a long-distance iPad talk. These things don't work as well as Blackboards. I apologize for that. But anyway, so I'm going to be talking about some work. Well, it's going to build up to work in progress with Carolina, Song, Jin, and Chi about the title, talking about a notion, how this picture of curves on surfaces generalizes kinematics in an interesting and important way, and allows us to talk canonically about integrands for gluon amplitudes, non-supersymmetric gluon amplitudes in any number of dimensions, which has been a long-standing dream of mine to try to understand. Some of the ideas that I'll talk about at the beginning, I actually talked about at the Amplitudes meeting last year, but the paper has not yet appeared. It was sort of worked out with Hadley and Giulio from last July about some of the systematics about how to think about these objects for the trace phi cube theory. Okay, so to begin with, I want to, for this audience, I don't need to tell you or remind you that singularities of amplitudes have long been the most important things about them. Singularities, poles at tree level, for example. And so this is, of course, our famous picture that there is a locus where the amplitudes factorize into the product of lower point amplitudes in an appropriate way. This knowledge of factorization lets us often, so first, this is some canonical fact about this rational function, which is the tree amplitude. And the knowledge of factorization lets us recursively determine amplitudes in tree amplitudes in a variety of ways. So, for example, there's the sort of famous fact, most elementary level, just at the 4-point, that you just make a general ansatz for the oops, I can't spell ansatz. General ansatz, and impose consistent factorization, and that determines the amplitude. And then at higher points, of course, we have things like BCFW and other sort of shifty ideas, where if we have some control of infinity in some appropriate way, we can use the knowledge of factorization to completely determine the tree amplitude. Okay, so that's a story that we're all familiar with, but it's worth pausing because I'm going to be talking about this point. I'm going to be stressing this point. It's worth pausing to remember that this already needed that factorization at tree level, understanding factorization at tree level, already needed an extension of our notion of kinematics. In other words, if we're most naively, if we work in Lorentzian kinematics, we can't see this. And that's because in Lorentzian kinematics, for any amplitudes other than those of a pure scalar theory, for particles with spin, gluons, for example, all of these 3 particle amplitudes just vanish in Lorentzian kinematics. And so we have to generalize from Lorentzian to complex kinematics already. This is a generalization away from, physics in order to have these amplitudes be non-zero. Okay, and to be able to run this whole program. Now, it's also worth saying, again, something we've gotten extremely used to in this business, that this is something that happens to us all the time. We begin by thinking about physical amplitudes with physical kinematics and physical principles like locality and unitarity. then we observe that sometimes those principles are imprinted on the amplitudes in some very recognizable and simple and clean mathematical way. For example, if we talk about the production of massive particles like a Z from massless particles on the outside, then so these are massless, but this is massive. Then indeed it's true that for this amplitude, asking for unitarity, so asking for the imaginary part of this guy to be correct. So unitarity at tree level for this guy really does tell us that it should factor into the product of producing this massive particle and having the massive particle decay on the outside. So this is unitarity. In this case, unitarity does imply factorization. However, precisely because these amplitudes are all vanishing in Lorentzian kinematics, related to the fact that we can't have two massless particles fuse into one massless particle without having everyone be collinear, you see, that's putting an unnecessary restriction on the momentum because we're demanding that we talk about them in Lorentzian signature. That's what makes the amplitudes vanish. And so four-particle factorization is not, strictly speaking, a consequence of standard unitarity because we don't even see it for normal physical momentum. This is part of the abstraction that we're extremely used to in the amplitudes business, that you see a mathematical property that comes from a physical principle, but then you abstract away from it. And so we think of factorization as a more primary and fundamental thing that sometimes implies unitarity, but also has other consequences, and we can use more broadly when we have complex kinematics. All right. So that's a familiar story, but I just wanted to remind you already that it involves a generalization of our notion of kinematics. I'll make one more comment at tree level, which is that we always say that factorization is this picture, okay, that the amplitude factorizes, but the precise meaning of this picture is often very intimately connected to, so the, of course, also for this audience, I don't need to stress that understanding these objects and their singularities is intimately connected to discovering some combinatorial positive geometry that might be capturing these singularities in a novel geometric way. But the precise meaning of these pictures is intimately related to precisely what the geometry is. And the geometries are, in the end, somewhat different from each other. And that difference is exactly reflecting the slightly different precise meanings we give to this picture. For example, if we're talking about trace phi cube theory, then we literally, what this picture means is literally simply the product of the left amplitude and the right amplitude. But if we're talking about n equals 4 super Yang-Mills, let's say in momentum space or standard spinor helicity superspace, then the meaning of this same picture involves an integral over the intermediate Grassmann variables of m left times m right. So it's not a straight product, it involves an integral. Finally, when we do n equals 4 super Yang-Mills in momentum twistor space, then again, the meaning of this formula is a little different still. The integral is gone, famously. We're still left with m left times m right, but if these indices are I plus 1, jj plus 1, we're also left with a little factor here, which is the 4-particle R invariant that tells you something about the way these points in twistor space are organized on the plane where I plus 1 and jj plus 1 intersect each other. So these are all roughly left times right, but the precise notion of what you mean by left times right matters and is reflected in the rather different forms of the geometries. Here we have the isosahedron, here we have the momentum amplituhedron, and then here we have the amplituhedron, the momentum twistor amplituhedron. Okay. So I'm stressing these points because when we talk about gluons, we're going to be talking about yet another avatar of what these formulas should mean, and so I wanted to stress this point already in a familiar setting. All right. Any questions about this before we proceed? I think this is all well known to everyone. Okay, so now let's talk about loop level. And at loop level, there's famously always been a problem. So first of all, at one loop even, at the higher loops, there's a zeroth order thing, which is that there's a notion of the integrand only in the plane of limit. I might come back to this point later, but there's the very zeroth order issue of how we can combine all the diagrams together and consistently label what we mean by loop momenta from one diagram to another. But at least in the plane of limit, this completely almost trivial aspect of the problem has a simple solution. I'll say a little bit more about it from the surface point of view in a second. But even let's put that aside, and that's not really an issue at one loop. It's pretty obvious how you deal with this issue at one loop anyway. But there's a bigger problem, which is at loop level, we want to talk, in addition to the singularities that look like this, where this is, let's say, one loop on this side and tree on this side, we want to have the loop cut. We want to have the singularities that correspond to a loop variable, just a single loop variable going to 0. Okay, so something like this, where we cut this guy. And the problem with this, so obviously, we're going to have singularities that look like that. And clearly, if we're putting this thing on shell, we have to interpret this as let's say, a tree amplitude with 2 extra particles with momentum L and minus L. Okay, so this is the loop cut or the single cut. And now you see what the problem is. Again, we're in the totally standard notion of kinematics. If we cut this loop open, these two variables on the underlying tree problem that we should get have momentum L and minus L, and we're screwed because this gives us, amongst other things, this tree amplitude should have this kind of part in it, where this is L and minus L, just like a T-channel for a process like this. And because this is in such a special locus of kinematics where the momentum equal and opposite, the momentum here is 0, and so there's a 1/0 in the answer. So you cannot possibly match the single cut, because the single cut is badly defined, right? It just blows up in this limit. Now, this is obviously related to the fact that the integrand itself has pieces that are funny, that we're very used to in textbooks. Like, it has diagrams like this. It has a tadpole diagram, for example. So this should be part of the loop integrand. And this is exactly the guy that if you cut it open, would give us this tree. All right. And so there also in the integrand itself, there's naively a 1/0. Okay. Now, here it's a 1/0, period, okay, if we have massless particles. If the particles are massive, you could say that it's a 1/mass squared, but it doesn't change the fact that this cut is only defined on this very singular locus in the kinematics. But in any case, we're interested in massless particles. We're ultimately interested in gluons, so we can't just willy-nilly give them a mass in this way, obviously. All right. The same issue arises with external bubbles. Okay, so it's a very similar issue arises with external bubbles, where again there's 1/0 naively from these guys. Now, why isn't this the massive problem in textbooks that obstructed people from calculating one loop diagrams since 1965 or whenever they started calculating loop diagrams in Yang-Mills theory? Well, the reason is that there's an obvious thing to do with these diagrams, which is to throw them out. Okay, you can throw out tadpoles, you can throw out massless external bubbles. They have various interpretations, but at the most basic level, they just vanish in dimensional regularization. So there are scaleless integrals. If you integrate over them, they just vanish in dim reg, and so it's okay to simply throw them out. Okay. So, so it does not obstruct getting the final answer at the level of the amplitude. But if you care about the integrand as some kind of perfect object, it definitely screws it up, right? You can't include them. If you include them, there's one of the zeros. And so that makes it, so it's A, ill-defined, and B, both the integrand is ill-defined and the cut is ill-defined. And if you throw them out, then obviously you can't match the cuts. Okay. So there is no such thing, therefore, as there's naively no the integrand, even though I can combine all the diagrams together. There's a consistent notion of loop momentum and so on. There is no the integrand, by which I mean that there's no object that consistently on single cuts matches to a lower point amplitude. Okay. This now shows up in Yang-Mills theory and the NLSM in a variety of additional ways. In Yang-Mills theory, it means that there's no gauge invariant integrand. And this issue in the NLSM means that there's no integrand that has the Adler zero. And of course, by now in this business, we're very used to the fact that the Yang-Mills and the NLSM are closely connected, and gauge invariance and the Adler zero are closely connected notions. Okay, so okay. Now, equally famously, in maximal supersymmetry, in n equals 4 super Yang-Mills, this problem is avoided. It's avoided because the sum, the supersum in these diagrams is 0. The supersum is 0. And so this means that the single cuts are well defined. And that means that the integrand is well defined. It exists. All right. And that's wonderful. It exists. And it's therefore A, so it exists, that this has two implications. A, we can recurse it. So that's what using all loop BCFW, for example. And that's important both for getting the answer and also for giving a target for the object that we should be able to sort of determine from some underlying geometry. And so B, it's the target for the loop Amplituhedra, which was what we then eventually discovered. Okay. But for less than maximal supersymmetry, no joy. All right. And I have to say that, of all the things in all these years thinking about this kind of stuff, the one thought that kind of bothered me the most, not beyond the planar limit, I thought these things are sort of technicalities. Something that sort of bothered me more was that even in the planar limit, even at one loop, going from maximal supersymmetry to the real world with the zero supersymmetry just had this obstruction in it, that there was no integrand, there was no good object, there was no canonical thing, nothing that was gauge invariant, nothing that satisfied cuts. What could the geometry possibly be? What is the object we're trying to determine, other than maybe the amplitude itself directly? But if we if we think that there's a hint to these amazing structures at the level of the integrand, then it just seems to be this zeroth order obstruction in getting to the real world. And I remind you that one of the reasons why these single cuts are well defined is that the only way to have them involves singularities at infinity. So for example, these the tadpole as a triple pole at infinity when you think about it in the dual momentum space. So somehow it seemed like the reason n equals 4 was getting away with it was because of dual conformal invariance that means that there's no poles at infinity. And so maybe all this stuff was intimately connected to dual conformal invariance in some way. Okay, so one of the usual criticisms of this business is that, well, you see all these wonderful mathematical structures because it's an integrable theory, it's not going to extend to the real world. 95% of me never believed that criticism, but 5% did, and the 5% that did was because of issues like this. Okay, so that's what I want to talk about today. I want to talk to you about what we think is a solution to this problem. But the solution to this problem is going to proceed along the trajectory that we've seen already, that we had to generalize already from a notion of Lorentzian kinematics, the complex kinematics. And we're going to have one more generalization of the notion of kinematics to the kinematics that's naturally associated with surfaces. Okay. Oh, sorry. Maybe I'll make one more comment before going on to this, which is that this issue really has teeth. You can see it in the fact that while we have these things like the recursion relations and the Amplituhedra and all this stuff for the integrand at one loop, higher loops for n equals 4 super Yang-Mills, when you talk about determining the integrand for pure Yang-Mills theory, which has been a huge program, wonderful, spectacular program at the LHC, our friends from the on-shell point of view, Lance, Zvi, and David doing all these amazing things with Black Hat, all this big machine for determining amplitudes at one loop, then it's always been a little bit funny that the ideas that go into that, they overlap with some of the ideas that we talked about for n equals 4 super Yang-Mills, but they overlap exactly on things like boxes, like for the leading transcendental pieces. And everything after that just goes off in a different direction. It has a totally different feeling. It has a feeling of making an ansatz, determining the coefficients. And then for rational terms, there's a whole other story. You have to talk about things in d dimensions, not just in 4 dimensions, or other techniques to determine the irrational terms. It does not have the same feeling of just one canonical thing. You just do the most natural, obvious thing, and everything works. There's this whole machinery that you have to build up around it. And so, of course, now in phenomenology, people, they consider this a solved problem at one loop. They're moving on to 2 loops. But I think we know that conceptually in the amplitudes business, you cannot move on until the earlier things are perfect and simple and canonical. And this has always bothered me because I felt that our understanding at one loop already did not have the character. Okay, so again, there's teeth. For example, whatever you're doing has got to somehow give you rational terms. And we don't know how to get rational terms without thinking about d-dimensional physics. They just come from epsilon over epsilon terms in dimensional regularization. Or if you're going to get them for more physical regularizations, you have to see massive states. But if you want to sort of play with purely massless objects, it's hard to see how you'd even see them in a purely 4-dimensional setting. Okay. So these are all things that have to sort of come out of some clean conceptual way of thinking about things. You also have to get the rational terms. You just got to get everything out of the kind of things that we're after. All right, sorry. So we think that there's at least one solution to this problem, and part of what I hope to accomplish in this talk is to motivate trying to find an analog of the solution more in the home base of the original Amplituhedron, which thinks about kinematics in a quite different way than what I'll be talking about here. But at least in the setting of the ideas we've been exploring recently, there is a generalization that goes from Lorentzian to complex to surface kinematics. And when we think about surface kinematics, we're going to find a notion of a perfect integrand. A perfect integrand, it's going to address all of these issues. And the reason is that it's exactly going to allow us to give non-zero kinematical meanings to these variables, so tadpoles and bubbles and other things. Okay, but we're going to have the perfect integrand. It's going to have correct cuts. For Yang-Mills, it will have gauge invariance. For the NLSM, we understand this at all loops already, and it has the Adler zero and more. So the NLSM is sort of understood at all loops already. And perhaps yesterday, Carolina, in her talk, may have talked about how we understand the Adler zero and various other extensions of it from facts about splits. But anyway, the fact that those things make sense means that the NLSM is I think just understood. But I'm going to focus then more about on Yang-Mills. So there's a perfect integrand. It has correct cuts. And it has good behavior at infinity, which is another slightly magical thing that allows us to recurse it. Okay, now this we've understood. This is now in the scalar scaffolding language. This is in the scalar scaffolding language. So we've understood this at tree level and one loop so far for Yang-Mills, and all loop is in progress. Okay. I hope you'll understand from the review I'll give just for the trace phi cube theory why this is a natural division, tree level one loop, and somewhat new ideas that show up for all loops. But this means in particular that there's a few line Mathematica code that just calculates Yang-Mills integrands at one loop. Okay, no big machine, nothing different for rational terms and this and that. Non-supersymmetric Yang-Mills integrands, any number of dimensions. As usual, even we're used to it in this stage of generalization, you go to these complex objects to determine the perfect thing. And then, of course, nothing stops you from specializing back to the physical one. Okay. And the same thing is going on here. We need to go to the surface in order to find the object with all the perfect properties. And nothing stops us from specializing the momentum all the way back to a physical ones to get the actual amplitude post-loop integration that we've checked, at least in examples up to 4 points, does actually work. All right, so that's the story that I want to tell you in the rest of the talk. But maybe we can pause again here to see if there's any questions. All right. All right. So okay. So let's continue then. So let me remind you of these surface integrals that we've been talking about. Okay, so there's an object. I'll call it. Let me call it an integral associated with any surface, which is the integral of the product of the positive parameterization y variables and the product of all the curves on the surface ux to the x. Okay, where these u variables depend on the y's. Okay. Okay. Now, so if we literally take this, this object, then in the limit as alpha prime x is much smaller than 1, we have this is the field theory limit, and I becomes the sum over all the triangulations of the surface of the product of 1 over x for all the x's in the triangulation. All right. Now let me step back for a second and emphasize a point. This is a point that we've been making in this surface story from the very beginning, but it really it becomes more vivid when we for the issues that we're talking about. You see, already at tree level, just the very fact that surfaces are important is related to the basic fact that the singularities are associated with curves on the surface. Okay, so I draw a curve on the surface x, but the poles of the amplitude are really not associated with points on the surface, but they're associated with curves on the surface, and the momenta are associated with homology. Okay, so I imagine giving the boundary curves some momentum, and the momentum of this curve x is a sum of all these momenta, because you can think of being able to deform x to the boundary. Okay, okay, so at least the zeroth occurrence of the notion of curves on surfaces is already there. With thinking about what the propagators are for Feynman diagrams, thinking what the momenta are, but in this avatar, it's homology of the curves that matters, the curves up to a homology. And already at tree level, we have the idea that the amplitude is the sum over triangulations. But here, there's no subtlety. We just imagine triangulating the surface, and every curve, the propagator is associated with the momentum that I read off from homology. But when I go to loop level, at loop level, it's crucial that if I want to think about the amplitude as a sum over triangulations, again, it's crucial that I think about the curves x up to homotopy, not just homology. And we see that, for example, if I draw a simple bubble diagram, okay, so this is something which is dual to this bubble diagram, okay? Okay, so let's say I'd even four points here, okay? So something like this, all right? So now here, in order to be able to capture this diagram and think of it as a triangulation, it's crucial that this curve and this curve are different, right? And this is the propagator on this side, and this is the propagator on that side, okay? So they're different as curves on the surface up to homotopy, even though they're exactly the same in homology, because the puncture carries no momentum, okay? So this is so if we want to have the idea that so we're drawn into the surface world by realizing that the kinematics are associated with curves on surfaces, but Feynman diagrams are associated with triangulations of the surface, where you think about the curves up to homotopy and not homology. So that's the basic generalization of surface kinematics. So surface kinematics tells us that we have to think about not momenta, which is homology, but something bigger. So an extension, which is the curves up to homotopy. And again, nothing stops me. So in other words, so the natural thing from the surface is just to assign to every curve C, I can assign some xc, and that's it. Okay, so that's what's natural from the perspective of the surface. Then I have the sum over all the triangulations of the product of the 1 over xc for every triangulation, and that's it. And again, nothing stops me from specializing the xc's to be given by the homology in order to go back to physical kinematics. But this is the thing which is most natural from the perspective of the surface. All right, now famously, infamously, if you've been listening to suffering through at least my talks on the subject for the past many years, there is an issue. There is a cost to this, which is an infinity. There are infinitely many triangulations. Beginning not at one loop, but beginning with not with planar one loop, but beginning with double trace one loop, or the annulus diagram, and then higher loops. The issue is that, for example, if I draw it for the annulus, that here's a curve on the surface. Okay, so here's a triangulation. Let me ignore these other points. But I can also take these guys and wind them around. Okay, just wind them around as much as I want. So after all, here's a curve, here's another curve, but this can wind around any number of times you want until it comes back to that point. And so I can start with a triangulation and then just wind it as much as I want. That's the action of the mapping class group. They're all the same combinatorial, they're the same Feynman diagrams, but they're different triangulations of the surface. Okay, so at least beginning with the annulus and to higher orders, if you're going to take this generalization of surface kinematics seriously, then the most natural first thing you're talking about is an infinite integrand. Okay, and you have to talk about how you're going to match this infinite integrand to physical amplitudes that we care about. But that's the zeroth order thing, is that there's an infinite there's the infinite integrand that you're talking about, and it's an infinity which is reflecting the mapping class group and has the infinite copies of all the diagrams that you have to do something about. Okay, now again, I stress this has nothing to do with planarity. It's there already starting at 2 loops, even for planar diagrams, because again, I have this curve, but I have this curve. I have all the curves that wind around any number of times, and these all show up in triangulations. Okay, so I can take pictures like this and wind them around as much as I like, even in the planar limit. Okay. Now, let me just make a couple of comments about this. Again, these issues arise at 2-loop planar and higher, 1-loop double trace and higher. So this is all about the action of the mapping class group. And first, in the case of the annulus, or generally non-planar things, the first thing I want to explain is we're familiar with this idea that planar integrands exist, normal kinematics, and something funny happens beyond the planar limit. Here, all surfaces are treated uniformly, so there's no fundamental difference. We can think about all of them in exactly the same way. There is a canonical way of labeling loop momenta, even if you're beyond the planar limit. That's naturally given by the surface, but we do have this infinity that we have to deal with. And so for surfaces like this, like the annulus, the mapping class group action, if you now think about the assigning the x's for a given curve, let's say a curve that goes from here to there but winds around some number of times w, then the x that's associated with this, if this curve has momentum L and the sum of the momenta on this curve on the inside, let me call it Q, then the x that you would assign for the curve that winds around w times is L plus WQ squared. Okay, so that's just what you get from homology as you wind around some number of times. And so under the action of the mapping class group, the loop momentum shifts. Just L goes to L plus Q. As the winding goes to winding plus 1, let's say the loop momentum shifts. L goes to L plus Q. So the integrand, this infinite integrand, is not invariant under the mapping class group. It's covariant, so you have to shift the loop integrand to keep the integrand invariant. But post loop integration, of course, because the loop integration is invariant under a momentum shift, the post integrated object is mapping class group invariant. Okay, and so we can talk about modding out by the mapping class group post loop integration. And that's what we talked about in the papers with Hugh and Pierre and Giulio and Hadley. That's exactly what we talked about. You do the loop integration, and then there's a procedure for modeling out by the mapping class group using the Mirzakhani trick, blah blah blah. Okay. Something that I want to stress here, because I think it's at least mathematically interesting, and it might be physically interesting, is that there's something else that we can do. There's something else that we can do that doesn't have the complexities of loop integration or anything like that. We can simply identify, so if I have 2 curves xc and c prime that are the same up to the action of the MCG, for example, in this annulus case, they just differ by winding. In the curve integral, curve integral, we can simply just give them the same x. All right. So in other words, just the exponents that occur, we can just declare are the same for all the curves that are the same up to winding, up to generalized winding. Okay. Now, for planar integrands, for planar surfaces, this object is exactly the planar integrand, and that's because when we have something like this, I have this curve and that curve, and the ones that differ by winding, these all have the same momentum anyway. They have the same momentum anyway, exactly because the punctures carry no momentum. So this object that we're defining, so you see here, I don't need to do any loop integration to mod out by the mapping class group. Okay, I'm going to define this integral I'm going to make all the exponents for the curves under the MCG to be equal to each other. And I'm going to mod out this integral by the mapping class group. No loop integration involved. Okay, so this is a very simple canonical mathematical thing that I can do. For the planar surfaces, just punctured disks, this happens to coincide with the loop integrand. Okay, that happens to coincide with the loop integrand because these x's in this case are the loop momentum. It doesn't beyond the planar limit because, as I just showed you, the loop momentum shifts when you interpret it in terms of loops, but it does for planar diagrams. Okay. So this is an interesting object that we can then talk about. So we can talk about this integral, which is now again just the integral of the product dy over y, product over x u x to the x. But here where I just identify identify all x's for curves up to MCG, and here I just mod out by the MCG. I can mod out by the MCG using the Mirzakhani trick or any other trick that you would like to use. But this is an interesting object that again, when alpha prime x is much small 1, is defined for any period is defined for any surface. Is defined for any surface. When alpha prime x is much smaller than 1, you can think of it as the sum over all distinct triangulations of the surface up to MCG. So this is really the same as all possible Feynman diagram topologies, okay, of the product of the one over x's. Okay, so we don't have the infinity simply because we're identifying all of the triangulations that are the same up to the MCG. Okay, so this is a nice object that we could be talking about. Again, in the case of for surfaces, in the planar limit, it coincides with what we would call the planar integrand for the trace phi cubed theory. And let me just make a couple of comments about this object. If we work with alpha prime x much smaller than 1, but also we just set all the x's equal to 1, we set them all like literally equal to each other, then we're just summing over diagrams, giving them all the same weight. We're summing over diagrams. And this is, of course, nothing other than the matrix model for trace phi cube theory. All right, so, but what this object is giving us is a double generalization of the matrix model, where instead of setting all the x's to 1, we set all the x's for curves up to MCG equal to each other. This double generalization has all the x's up to MCG on the one hand, and it has an alpha prime on the other hand. Okay, so for example, you could keep all the x's equal to 1 and just turn on alpha prime. So this is some interesting stringy deformation of the matrix model. I don't know what it means. I don't know what its physical or mathematical properties are, but amongst other things, already at tree level, it gives a stringy generalization of the notion of Catalan number. Okay. On the other hand, I could keep, if I turn off alpha prime and I keep all the x's distinct, then it gives me this thing that in the planar limit is the planar integrand. But it gives me some object also for non-planar surfaces. And of course, the double generalization is the most interesting of all. But I think if you're a mathematician who's sort of interested in these things, this is a simpler object to think about. I suspect it's going to have lots of interesting properties, but that does not involve the extra complexities of the loop integration and the surface semantic polynomials and all of the rest of it. I say all of this, I took a little too long saying it, but I said all this because I wanted to tell you something about how we can think about the singularities of this object that again coincides with the planar integrand, at least in the planar case. So let's call this function when alpha prime x is much smaller than 1. Back in July with Julian Hadley, we called it the good function for a surface x. So it's a function of all of these x's for all the curves up to the mapping class group. At tree level, just sum over the tree diagrams. Loop level, just sum over the loop diagrams as we're used to, because there's no action of the MCG in those two cases. And so we're used to thinking that the way we should characterize this is in terms of singularities. Okay, so what happens as some x goes to 0, for example, is that the G for a surface, again, at tree level and in one loop, we normally say it goes like 1 over x times the G for the cut surface. Okay, where I cut along x. So for example, at tree level, the cut surface would just be these two guys when I cut along x. Okay. However, and this is another one of the sort of problems when you think about non-supersymmetric theories. Starting at 2 loops and above, again, even in the planar case, it's clear that it's not enough to just think about singularities as single poles. And the reason is that the integrand simply has double poles in it. Okay, so again, I can have a diagram like this. Here's a nice triangulation. Okay. And so you see, this of course involves tadpoles and bubbles, but you see it has this curve and this curve in it. These two curves are the same up to MCG. So if you're working in the infinite integrand, everything is simple poles, everything is fine. So the infinite integrand is totally canonical, very normal, simple poles. But this guy has double poles in it because I have this guy and that guy occurring together. And they're really the same up to MCG. There's nothing I can do about it. Okay, so that even the planar integrand for the trace phi cube theory has double poles. And so it's not clear how you should be thinking about characterizing the singularities. Of course, that's double poles, triple poles, arbitrary poles as you go to arbitrarily high loop order. It doesn't seem like it's as canonical as we thought, where we just specify the residue as the propagator goes to 0 because we have double, triple, arbitrarily high poles. All right, it turns out that this question has this question of how to characterize the singularities has a very beautiful answer that, practically speaking, also gives us directly a formula that lets us recursively calculate these good functions for any surface just with a shift enter on the computer. So practically it gives us the planar integrands for the trace phi cube theory, as well as any color theory, arbitrary polynomial interactions. But I'll talk about just the trace phi cube. But here's the central idea. We can see the central idea already at the tree level. You see, at tree level, these good functions, we normally think of functions of x's as the sum over triangulations with the product of 1 over x's. Okay. But I'm going to make, and so here the statement is what happens as x goes to 0, I pull out a 1 over x, and then I get a g cut, just as we talked about. What we're going to do now is slightly change our point of view and talk instead of x's in terms of, I don't know, let me call them little x's, which are 1 over capital X. Okay, so from this way of thinking, now I have G surface as a function of the little x's, which is now just going to be polynomials. Instead of having poles, they're going to be polynomials in these little x. At tree level in one loop, they're at most linear in these little x's. At higher loops, they have they have squares, cubes, higher powers. That's just what we had talked about before. So what I was complaining about is that we don't know how to characterize the notion of singularity as we approach these capital X's go to 0 at the higher loops, because there's double, triple, higher poles. But it turns out that when you switch the point of view to the little x's, just the inverses, there's a uniform statement for all surfaces, which is the following beautiful statement, that these good functions satisfy a differential equation. That if you differentiate with respect to the little x variable, the good function, then this is a thing which is equal to g cut. Okay? So obviously, at tree level in one loop, this is the same as statements that we know and love, because the dependence on the x's is like capital 1 over capital X anyway. So if I flip and I think about the little x's upstairs, then all I'm doing when I differentiate is pull out the pole that multiplies them anyway. So a tree level in one loop, this is exactly sort of trivially the same as the way we think about singularities. But this formula ports to all loop orders, okay, and all surfaces. And you can use this formula clearly to compute the amplitude, because all you've got to do is integrate this differential equation. You just have to go to some place where you know what the amplitude is. For example, we know for trace phi cube theory that when the x's are equal to 0, which is when the capital X's go to infinity, that the amplitude vanishes. So this function vanishes because everything just has 1 over capital X's in it. Okay. So that means that there's a point here where everything is 0 that we know. We're trying to get to a point for a bunch of x's, x1 through xn here. So all I've got to do is take any path from 0 to there. For example, I can rescale all of them by common t and just integrate this differential equation. The g is g of 0 plus the integral from 0 to wherever I'm going, dg, and dg is given by g cut. So in this way, and this is 0. So in this way, I can recursively determine the all loop, all surface good function. And again, in particular, for the planar, in the planar limit, this is the standard planar integrand. Okay. So this switch in point of view from thinking about poles to differential equations that these objects satisfy in terms of the inverse propagator variables is what allows us to do this and determine what these integrands look like to all loop order. Okay, so now I have 10 minutes left, so I want to say something about gluons, but just to take a stock, what have we seen? So we've seen that to think about that we're drawn into thinking about surfaces to begin with, because even at tree level, kinematics are associated with curves on surfaces, but associated with the curves on surfaces up to homology. But thinking about Feynman diagrams forces us to think about curves on surfaces up to homotopy. The most naive thing to do with that will give us these infinite integrands when we go beyond one loop and the planar limit. And that's a perfectly fine object. There's nothing wrong with that. But if we want to go back towards physical amplitudes, we have to mod out by the mapping class group. We can always do that post-loop integration. We can do that pre-loop integration in the planar limit. And also purely mathematically, for any surface, we can define this good function for all surfaces. And we learned that instead of characterizing the functions by their singularities, if we want to go beyond one loop, we have to invert our way of thinking and characterize instead by this differential equation that these good functions satisfy. That I don't have time to show you, but really practically gives you, with a push of a button, very high loop, very high multiplicity integrands for this theory. Okay, so now I want to move on to talking about gluons. And so this is scalar scaffolded gluons. And as all that happens in this story is that it's exactly the same integral, except that instead of the measure being the product of dy over y, it's the product of dy over y squared. Okay, so that's the that innocent changing from the measure dy over y to dy over y squared is what gives us gluons. Okay, so that's the crazy thing. Technically speaking, this is gluons in the scalar scaffolding picture, but mathematically these y's are associated with some triangulation of the surface, and so we're going to be talking about a surface with 2n extra particles where the triangulation looks like this. So it looks like we triangulate an inner part and we just add these forks on the outside. Okay, so for this particular kind of triangulation, simply changing the measure from dy over y to dy over y squared gives us a description of gluons, where to see the gluons, we're supposed to go on the pole where we set all of these variables to a 0, and we physically think about that as the scalars on the outside producing gluons on the inside. Okay. Now, so in a sense, we're done. Okay, this is the claim is that this is giving us gluons at all loop orders. The challenge is to understand how to get something practical out of this, and also something conceptual out of it. So the main question is, how do we take the field theory limit of this? And the reason it's more challenging is exactly that we have this a non-logarithmic form. We have a dy over y squared rather than a dy over y. Now, so I think it's a beautiful problem, because of course if I naively take this integral from 0 to infinity, it's power divergent, not just logarithmically divergent. So it really needs analytic continuation. I think this is a beautiful problem because there's all kinds of systematic methods for doing these analytic continuations. All of them look horrible. And I strongly suspect that the right answer is not going to be something which works for totally generic integrals, but something that does something very special and specific for this guy. Okay. But let me tell you at least one way to take the field theory limit that does tell us something qualitative. Which is that which we already see in the simplest example. So if we have this the example of 4 points, something like dy over y squared, and then a y to the x13, and this is the 4 point minus x13 plus x24, but there's a dy over y squared here. Of course, this is gamma of x13 minus 1, gamma x24 plus 1 over gamma x13 plus x24. And if I call this guy C13, as we like to do, this goes to C13 over x13, okay, at low energies, okay, when all the x's are small. Okay, but let's see how we can understand this directly from the integral. So I'm going to divide the integral up from 0 to 1 and 1 to infinity. And the only divergence here, the interesting one that we're talking about, is from 0 to 1. So I'm going to call this negative C13. So let's forget about the other part. You can think of this division, if I put y equals e to the minus t, this takes me to the world of the fan. And you can think of this division as literally in the fan. There's a sort of origin here, t equals 0 in this case. Okay. And so I have this region, which is y between 0 and 1, and this region where y is between 1 and infinity. Okay. So let me focus on what's going on in this part of the fan. And so what I do is I just take this integral 0 to y, dy over y to the x13, 1 plus y to the minus c13 to the y squared, and I simply Taylor expand this guy around y equals 0. So this is integral 0 to y, dy over y, y squared, y to the x13, 1 minus c13y plus dot, dot, dot. And now you see what happens. This first naively power divergent term, well, if I actually integrate it, is 1 over 1 minus, 1 over x13 minus 1. Okay? And then the next term has the normal logarithmic divergence in it. So the next term looks like plus C13 over X13. I'm screwing up the signs, I'm sure. And then I have plus dot, dot, dot. But crucially, this term does not have a field theory limit. Okay? I mean, it's subleading in the field theory limit. And so you see that the term that dominates in the field theory limit, you have to keep expanding. You have to keep expanding these exponents, and it looks like this. All right. Now, so this tells us that this is a general phenomenon, but it tells us something very interesting. It tells us that that when alpha prime x is much smaller than 1, that these integrals look like the following form. They have 1 over x's downstairs, but the numerators are made out of c's. So we call this a C expansion. Now, you don't have to have for trace phi cube theory, the things upstairs are 1, and downstairs you just get the product of all the propagators. For Yang-Mills theory, you can get any number of x's downstairs, including no x's downstairs, so purely c's upstairs. But this is a very non-trivial fact. The fact that the amplitude can be expressed in this way, where you have normal poles downstairs, but the numerators are C's, makes a claim about a vanishing at infinity of multiple residues of the Yang-Mills amplitudes. They all go to a constant as you go to infinity set by these C's. And that also tells you that there are special directions that you can shift where the integrand vanishes when you go to, where this object vanishes when you go to infinity. Okay, so this is what we can learn already at even at tree level, and this already gives new recursive ways of determining the Yang-Mills integrand at tree level. Now, whoever the organizer is, can I have 5 more minutes?
Yeah, sure.
All right, great. Okay. So, but this is really all. This is really all that this is all that we can easily say on general grounds. It's already not non-trivial, but we still don't have an especially good way of determining what this object is without this work of doing some analysis, sort of cone by cone, in thinking about behavior at low energies. However, what we can do is understand something about the factorization properties. What we can do is understand something about the factorization properties. And here, already even at tree level, so we know that if you set some xab to 0, you know that if you set some xab to 0, that the amplitude in conventional language should sort of now it has some mu index, but it should factorize some m right, m left, m right eta mu nu. Now, just like we're used at tree level to like using unitarity to derive something about factorization, here we can also take the standard momentum space way of thinking about the amplitudes and figure out what this means in the language of the curves on the surface, the language of x's. Now, at tree level, there's no subtlety. And at tree level, you can work out that what this factorization turns into is the following interesting formula where you sum over the indices sort of j on this side and capital J on this side of something that looks like xjj minus xja minus x capital JB, dm left by d, but now I have to do something that looks a little bit funny. Put an x prime here and an x, x j dm right by dx prime little j. Okay, so you see, everything has got to be described in this scaffolding language. So this lower point surface, I have to, I'm producing this intermediate gluon by adding this funny extra particle, this extra dot here. And similarly, so that's on this side. And then I'm adding this funny thing on this side, okay? This, taking the derivatives with respect to the x's is effectively pulling out the dependence on the polarization vectors in the standard language. Okay, so this is what factorization looks like already at tree level in this language. Now we can ask, where could such a funny formula come from? I mean, and very beautifully, this surface picture just hands it to us. So this is the point that I want to stress, is that you can start thinking directly in momentum space about what you expect the cut to look like. It should look like this at tree level, exactly like this. There's no subtleties at tree level. But then you go back to the surface integral and you ask, where can this come from in the surface integral? And the surface integral proves this for you. It hands it for you as a consequence of properties of the u variables. I'll summarize what those properties are. But once you get them, you can then see what it means on its own, in its own terms. And when you go to loop level, this is going to include all those curves that don't have a standard meaning in momentum space. Okay, so exactly the point that I was making at the beginning, is that when we deal with curves on surfaces, this is a perfectly legitimate curve. That's a totally legitimate curve. We can call this curve, we can give it a name, x11. Okay, it's a nice curve. This is a perfectly legitimate curve. We can call that one x41. So all of these curves exist. In normal momentum space, we have to set them to 0 by homology. But on the surface, we don't have to set them to a 0. We will not set them to a 0. However, the notion of what we mean by cuts is not borrowed from Lagrangians. The notion of what we mean by cuts is handed to us from the surface itself. And the correct notion of cuts has all of these guys in it. Okay, the correct notion of cuts has all of these objects in it. All right, so that's and all of this follows from very basic facts about U variables. Since I'm out of time, let me just tell you at least roughly what the structure of these facts are. So here's a natural question. Let's say you have a surface and you have some kind of road in the middle of the surface. It's a natural question to ask, how do the U variables depend on this road? Okay. So let's say I say it in the language of the fat graphs. I have some surface with some left part, some right part, and some kind of road here in the middle, y. It's natural to ask, how do U variables depend on y? And especially since I have this dy over y squared measure, if I have if there's an x associated with this road, I take this ux, this particular x. If I want to know what happens as x star goes to 0, the residue is simply given by taking the residue of this form at y equals 0. And so because of the squared there, I need to compute the d log of the u for any other curve with respect to y. So this is the object that I need to learn how to compute. Okay. Obviously, if I have curves that only live on one side or only live on the other side, they don't even pass through this road, so they don't depend on it at all. But a generic curve that passes through here will do something here, will pass through this road and do something out there. At the level of the words that we've talked about that characterize these curves, there's some word here, it does something, then it has a y in it, then it's going to do something else. Okay, and it's very simple to show from the counting problem definition of the U's and in terms of products of the matrices that exactly this object, the d log of U for a curve evaluated at y equals 0, precisely beautifully factorizes into the product of the d log of two other curves, okay, at y equals 0 times the dy of the log of a u on the curve right at y equals 0. But what are these two left and right surfaces? What are these two left and right u's? It's exactly what you get here if at y on one side you just stop by going down, and that's this factor. And for this factor, if you do the other way, you go down from y and then you do whatever it does on the other side. Pictorially, this means that if you have a curve that sort of crosses through, if you have a curve that crosses through this one, then what looked so funny in this previous picture that I have to add these things that sort of scaffolded on both sides is actually very natural here. Because it crosses through here, it's like I've added a point here. This point is kind of splitting the left surface by adding this scaffolding on the left with some point here x left and a point x right on the right. And this factorization of the U variables is exactly telling me that the d log of this blue curve becomes the product of the d log of the curve that lives on this side of the surface to x left and the curve that lives on the other side of the surface that goes to x right. Okay, so it's this fact about the factorization of the d log of the U variables. This is an extension of the binary property that we're used to. It's the refined statements now about derivatives of the U variables as well. That statement and sort of slight exceptions or differences to them when what lives on the right of this word is just a pure boundary. So if this goes up forever, then there's a slightly different formula. But anyway, there's simple canonical facts about the U's tell you what these derive these factorization formulae for you. They derive what these factorization formulae are for you on when you're exchanging a particle, and they derive what it is when you're cutting a loop open. Okay, so there's from the properties of the U variables, there's a completely well-defined intrinsic notion of what cuts look like. There's also a completely well-defined intrinsic notion of what gauge invariance means and multilinearity means. Okay, so all those things that, again, the hints for them, the clues that we're looking for something start in momentum space, but the correct formulas are handed to us from the surface, independent of any motivation for looking for them or what they should look like coming from momentum space to begin with. Okay, it's this fact that allows us to say the integrand exists, A. B, it has well-defined notion of cuts, both for the sort of tree-like cuts as well as for the loop cuts, a well-defined notion of gauge invariance. And so that's wonderful. That's exactly what we were looking for. Okay? We wanted an object that exists with well-defined notions of cuts and gauge invariance. The final point is that it actually vanishes at infinity in a simple limit. And this is very simple to show as a consequence of the C expansion that I mentioned before, that already is there a tree level, as I mentioned, lets us recursively determine the tree amplitudes in X language. This is not BCFW. This is another way of determining the amplitudes recursively in X language. You can also do BCFW, but this is a way that's sort of intrinsic to this picture. The same philosophy tells you a direction that you go into infinity where things are guaranteed to vanish at loop level. And so since we know what the cuts look like and that it vanishes at infinity, we just have a formula, the concrete formula that just lets us recursively determine the this perfect integrand. And so let me just end by showing you what these formulae look like. Okay. So down here to begin with, up here is what the 4-point tree amplitude looks like in X language. Okay, here it's just all been expanded out. But it looks a little bit complicated, but that you just have to get used to that. We're dealing with things in D dimensions. There's no helicity. There's no helicity sectors. The amplitudes just are somewhat more complicated looking, and that's just life. So this is what the 4-point amplitude looks like. It also doesn't look like such great shakes if you write it in terms of momenta and polarization vectors. But in any case, the length doesn't matter. At least conceptually, we understand exactly where it comes from. Okay. Now, the crucial point is that now we can take this information, I didn't mention, but this direction, the things that vanish at infinity at loop level, lets us only shift the loop variables. And therefore, our recursion relation determines the answer as a sum over single cuts alone. For an endpoint amplitude integrand at one loop, we just sum over all the single cuts. All this business about surfaceology is really telling us the following important thing, that if I think about a loop amplitudes, and I imagine cutting here, right? Well, this is supposed to be given by a tree where I imagine, cutting this guy open, okay? With two, I imagine cutting this open with 2 extra lines like this, okay? Of course, here in this language, everything gets extra scaffolded. So I imagine that there's little I'm scaffolding these extra gluons, okay? These 2 gluons. But the crucial thing, the absolutely crucial thing, the fact that on the surface I'm allowing this variable x11 to be not non-zero. That variable x11 is a perfectly legitimate variable on this tree surface. It's that variable on the tree surface. Okay, this bubble here is a perfectly legitimate variable on the tree surface as well. Okay, every variable, every curve here descends to something that is sensible on the cut surface. Let me emphasize the point again. Working with the surface kinematics means that we really are taking a codimension 1 restriction. I'm putting 1 variable to 0, and I have the variables that I have left allow me to access completely generic kinematics for the cut surface. Okay. Apart from the variable that I'm cutting, that I'm setting to 0, that becomes a boundary on the cut surface, all the other curves that are compatible survive on the cut surface. This is fundamentally different than the notion of forward limit. when I take forward limit, as I emphasize, we're forced to take the two momenta to be equal and opposite to each other, and then we're dead because we're putting a huge restriction on the lower tree problem, so restrictive that it's forced to blow up. Okay? Here, by going to the surface and keeping all these curves, including the funny curves that are naively assigned zero momentum by homology, we get to be sensitive to what the cut object looks like for completely generic kinematics of the cut object. Okay? And so this is what the 4-point tree looks like. And this is what the 2-point bubble looks like. This is the 2-point bubble integrand. So now again, it looks a little bit, complicated, but this precisely has, I mean, the point I'm making is that you cannot really think of this as coming from summing these diagrams. Again, in momentum space, it would be 1 over zeros here. But from the surface, you get something completely legit. It has pieces in it that have the normal structure. See, these kind of terms look like normal diagrams that look like that. But we have all kinds of terms here that have x's downstairs. So that's like a tadpole. This is a tadpole, right? But you see, it's not just something dumb like giving a mass to these tadpole propagators. These x's also appear upstairs all over the place. Okay, they occur in some consistent way everywhere. In fact, they occur in such a way that on a cut where you set one of the y's to 0, you exactly get the gluing of this 4-point tree object in the way that it should. Okay, so in other words, this has the property that if you cut this variable, you really get the 4-point tree amplitude where these things are glued to each other, but the surface tree amplitude and the surface notion of a gluon, which is the more general one. So, of course, once you have this integrand, so you can determine its integrand recursively. As I say, you can determine it in principle any number of points recursively. Once you get it, you're free to go back to ordinary momenta. If you go back to ordinary momenta, you have all these x11s and x21s and these tadpoles and bubbles downstairs. But of course, they're guaranteed to multiply scaleless integrands that will integrate to 0. So at that point, you're free to throw them out if you like, and only integrate the part that doesn't have them downstairs. So you're perfectly allowed to do that. But the natural object that comes from the surface has all of them in it and has these perfect properties. So I'll just end with a challenge that, in a sense, the starting point from the surface and this dy over y squared form is guaranteeing that all of these things are going to work. We can, in fact, derive what the precisely correct notion of cut means for both the tree cut and the loop cut, starting from the surface picture. But apart from that, at least at the moment, merely writing down this integral does not make it easy to extract the low energy limit. Instead, what we can do is abstract these properties away about the cuts and discover directions that the integrand vanishes at infinity to determine it. In this sense, we're in the same spot we were in 2009, 2010, when we had from all loop BCFW a way of determining the n equals 4 integrand, but not a picture yet for what that integrand by itself precisely was the answer to, until we discovered the Amplituhedra at loop level. So I think we're in a similar situation. We do have a parent for where these things come from the surface, but taking the field theory limit is not totally trivial. On the other hand, it's controlled by objects that have a completely well-defined notion of factorization. You see, you should add this notion of factorization to this list that we just talked about, both at tree and loop level. Now there's yet another way. There's a surface way of talking about what we should mean by tree and loop factorization. But we don't, apart from thinking of it as a low energy limit of this surface integral, which may be the only way of thinking about it, but it's conceivable that this beautiful rational function of this extended kinematics is itself the answer, just all by itself, the answer to some beautiful combinatorial geometric question that would give us a real analog of the Amplituhedron for these for this way of thinking about non-supersymmetric gluons. All right, I'm sorry I went on so long. Thank you very much.
Do we have any quick questions?
Yeah, so can you hear me?
Yes.
Okay. In terms of kinematic identification, what do you want to do with self-intersecting curves?
Oh, great question. Oops. Yes. So in fact, the self-intersecting curves give us the most perfect notion of kinematic. In fact, so let's say we're just talking at one loop. Okay. So at one loop, what are the variables that we're keeping? Okay. At one loop, we have these guys. You know, so we have these guys and these guys. So this is already something. We have xij and xji. And these have exactly the same homology, but xij is not necessarily equal to xji, okay? So one consequence of this, so just what we talked about already. So I'd have things like x11, and what you could call, so let's say this is x1n, let's say. And so x1n, that goes around the puncture. Okay, so and these are the kind of variables that you would naively think about if you don't have self-intersecting curves. There's a variable like n1, but n1 is genuinely a boundary. Okay, xn1 is genuinely a boundary, so naively we well, we don't have it. There's no variable associated with it. But what's really cool, as you anticipated, and I didn't have time to talk about more, when we talk about gluons, we have to keep the curves on the surface at least up to self-intersection 1. And so it's very beautiful that while there's no curve that looks like N1, that's not self-intersecting, there is one where it is self-intersecting, this one. Okay. So in fact, we do have xn1. We should add xn1s. If we're taking our philosophy consistently, we should add everything. And so the general philosophy is that you add all the curves of even if we keep higher self-intersection, all the curves where they only differ by self-intersection will be given the same x. In this case, since we're only keeping things up to self-intersection 1, then we add this xn1 as well. And so this is the set of all the kinematics that we're talking about. And crucially, even you need to add these xn1s in order to have everything be 100% trivial. Okay, so that the formulas for the cuts and factorizations, everything is follows completely directly from this factorization of the d logs that I was talking about. Okay, there's some minor interesting points that, I mean, the surface just tells you exactly what the answer is. You have to take it. But you really need to put all these curves in as the surface tells you in order for the answer to be interpreted in the simplest and most direct way. So that's what we do. Again, when you go back to momentum space, you're allowed to set this to 0, you're allowed to set that to 0, you're allowed to set that to 0. You can set these things to 0 if you like. At the level of the integrand, they'll give you 1 over zeros, but there'll always be multiplying things that are scaleless. So you're free to throw them out if you want and integrate the rest. But if you go back to this, the formula I was flashing at the beginning, you'll see it actually contains everything. It contains x. It contains things like x41, but also things like let's see, did this one contain everything? Maybe this is then, oh yeah, sorry. It contains x41 and x14. Okay, so it contains both kinds of objects in it. Did that answer your question?
Yes, it did. Yeah, thank you.
A quick question. Could you mention, is there any combinatorial connection between the good function and the surface? Is there any invariant from the surface? I don't know, connection to, I don't know, other cluster algebras or
I don't know. I think again. So this is a fascinating rational. I mean, it's a fascinating polynomial associated with any surface. Okay, so associated with any surface, there's a finite polynomial because there's a finite set of curves up to MCG for any surface. So there's a finite polynomial that satisfies this differential equation, and we can determine it. I don't know what it tells us about the properties of the surface. I think, as I said, I think it's a really interesting object to at least mathematically explore. The fact that there's it generalizes the matrix integrals is very interesting to me. So you said all the x is equal, alpha prime to 0. It's just matrix theory. But there's both alpha prime and this ability to turn on x's for all the different curves, and this guy's got to mean something. I would especially be fascinated to see what the extension of this differential equation is to include alpha prime corrections. That would be extremely interesting to try and understand. But at the moment, I don't know. You're asking if it tells you something about some, I don't know, some topological property of the surface, something. I don't
Invariance of the
know.
surface.
Yeah, some invariance of the surface. I don't know.